So thank you very much for attending this new webinar. Today we are going to talk about additive manufacturing of stainless steel 316L, and especially we're going to focus on the new filament we have released a few weeks ago, and we're going to try to explain to you what's new with this material and what's different, and what it will allow you to do compared to what we used to offer previously. For those that don't know us, we'll start very quickly with a short introduction on the company, and then I'll dive more deeply into this new filament, talk a bit about how to print, debind, and sinter the material, and then a few examples of use cases so that you can see what can be done with this material. So the first thing is a few words about Nano itself. Nano is a company who specializes in advanced materials for the industry, not only 3D printing. 3D printing is just one part of our activity. We also focus on ceramic raw materials and ceramic powders. We've been active for more than 50 years now, 15 years in that field. 3D printing is a more recent branch of the company. We've launched the Zetamix brand a few years ago in 2018. So that's been 5 years now, where we specialize on material for 3D printing, and especially filaments for 3D printing. The offer we have is a line of ceramic and metal filaments. Well, I should say ceramic, metal, and dielectric filaments now. The ceramics including alumina, zirconia, black and white, and silicon carbide, and metal being stainless steel and tool steel. We're a material company, so the core of our offer are the filaments. We do offer equipments for printing and processing of these filaments. Even though we're not a machine manufacturer, this is really important because there is a close match between the material and the post-processing equipment, especially for metal. The pair of the material and the debinding and sintering equipment is very important. So how does that work exactly? Well, for those who have seen a few webinars from Nano, you already know about this, but allow me to reintroduce a bit the technology. So the filament is basically a mix of binders and a powder, the powder being ceramic or metal, but that's really very similar. And the binders are here to allow shaping through 3D printing. They are here as a temporary binder. And usually there are several different components in the binder, and you will understand more about this later on. Typically, the volume ratio of powder versus binder is 50-50. In volume, in mass, you usually have much more powder than binder, of course. And then these materials are printed, debinded, and sintered. In the case of ceramics, the debinding is chemical in acetone, and the sintering is done in the air. There is an exception, which is our line of dielectric filament, which are materials that are not designed to be sintered, so they're just printed and used as they are, but this is for a different application, and I'm not going to focus on this too much today. If you want to know more about this, we did a few webinars previously, which are available on our YouTube channel. And so today we're going to focus on metal and how we use our metal filaments, how we process these and then use them. So the big news on these filaments is that we've decided to go back to a chemical debinding system for metals. We used to do thermal debinding. We decided to go back to this for a few reasons. The first one is it allows for a material that is easier to print. It allows for more complex geometries with less deformation, and also, and that was really the main reason we decided to go there, it allows us to do sintering under argon or hydrogenated argon, whereas we used to need full hydrogen atmosphere for 316L, which was really a major drawback. So that basically makes it much more affordable and accessible to any kind of laboratories and industries with relatively simple furnaces. You can start printing stainless steel, and that's really something new. Most stainless steel materials on the market at the moment usually use hydrogen sintering, and we feel that's a limit. We wanted to overcome that. So how does that work? Well, it really does look a lot like the metal filament snow. That means we print the part, we debind it in acetone, just like we used to do for ceramics. And then the only difference is that sintering is done under a flow of argon or hydrogenated argon. But the important thing here is that we've removed the need for pure hydrogen, which was really a significant limitation of the technology we used to have before. So we'll zoom up a bit on the different steps. The first step for printing is, of course, preparing your file. We have some very detailed guidelines. I'm not going to go into details of these, but guidelines for printing and design guides so that you don't try to print something that won't come out well from the process. In these guidelines, we do give some of a scale factor that you need to apply to the part in your slicer to make sure that you end up with the right dimension to compensate the shrinkage. And then, well, you can prepare your file and print the part. Then we'll go through debinding and sintering. I told you at the beginning that there is usually two components in the material, what we call a backbone and a soluble binder. The reason being that we talk about chemical debinding, but actually the debinding is a two-step debinding. You'll have a solvent extraction where you remove one of the two binders, and the second binder will be removed in the thermal process. So when we put the part in the furnace, we will burn out the rest of the binders and then densify the part. So practically it means two steps, chemical debinding and then thermal treatment. Physically, we could say there's three steps. There's chemical debinding, thermal debinding, and then sintering. Then we go for sintering. Sintering usually gets to high densities for ceramic, typically in the range of 99%. With metals, we are a bit more limited. We will reach 95% in ideal conditions. We feel it's good enough for the applications we have for this material, but you should be aware of that. Of course, having such a densification means you'll have shrinkage. In the case of metal, it's not precise here, but in the case of metal, it is in the range of 15% of shrinkage. And you will need to compensate for this in the slicer. That's an absolute necessity. That's also one of the limitations of the technology. This shrinkage can induce deformation. It can lead to slight variation in tolerances. Well, most of the limits of the technology comes from sintering and not from printing. Just to remind you of what happens when we do sintering, well, there's no miracle involved here. We're not melting the metal. Of course, if we were melting the metal, we would lose the shape. We are densifying in a solid state reaction, and again you see here what kind of happens is some coalescence between the grains and coarsening of the grain size. So to give some more information about this filament, you have a few info on the composition itself and density and all these. What you can remember is that in the case of stainless, we have a very high proportion of steel. The proportion indicated here again is in volume, so you have 60% in volume. In mass, it's more than 90%, close to 95, I think, because the stainless steel is much more dense than the binders. But the important thing is the volume percentage. It gives you quite a high density. The filament itself before sintering has a density of 5. After sintering, it's going to go up to 8. And well, the rest is, let's say, details for advanced users. A few information on the printing recommendations. Material prints at really low temperatures in the range of 120 to 130. Well, it's actually a mixture of printing recommendation and design recommendation. Speed of the printing is important. We usually print at relatively slow speed. Anyway, the process will be long before debinding and sintering, so there's no hurry on the printing side. And printing too fast can lead to unsuccessful prints. On the design side, there are a few things. One of them is the risk of deformation because of gravity. So you can't have walls that are too high, or they will collapse. You can't have too small details, of course, and you can't have too much overhang without supports. That's really important because you could print more than 35-degree angles, but then you'll have problems doing sintering. So that means when you're printing parts with overhangs, at some point you will need to have some supports, both for printing and for sintering. In general, we do have a detailed guideline and design guides. I really do recommend you to refer to these. They're going to be more detailed than what I can say in a few words. A few more examples here. Minimum hole size is in the range of 1.5 millimeter. Pin sizes less than 3 millimeter, you may have risk of collapsing during sintering. We tend to avoid sharp angles if possible. We do recommend the use of a flexible plate to remove the parts. And one of the last thing is you will need to use a slicer that allows for alternating directions of the shells at each layer, or you will have distortion. You have a small picture on the back, on the bottom right corner, where you can see a part printed clockwise, anti-clockwise, and another one without these clockwise, anti-clockwise alternating shells, where you see the kind of deformation you can have. Binding and sintering. Again, we have guidelines for this. I do recommend to follow these. What I can say is that it's really important to be fully debinded, both to avoid cracks and stuff like that during the drying phase, and also to avoid deformation during sintering. So you need to be fully debinded. There's usually no risk in being too much debinded. That never happens. So in case of doubts, I would recommend to keep the part in acetone for a longer time. Nothing bad will come out of it. So really make sure that you have a complete debinding. Typically, you'll have a mass loss of more than 4% of the mass should be removed during that process. We usually put the part in acetone, and then heat up the acetone to 30 degrees Celsius, keep for a few hours depending on the thickness of the part, and then cool down the acetone before removing the part. That's the ideal situation to avoid any deformation and cracks. Regarding sintering, of course, we're limited by the size of the sintering furnace, the size of the tube, which is a tube of 90 millimeter internal diameter. It's 100 external, 90 internal, with a heated lens of 200 millimeters. So that needs to fit into that that space. Sintering temperature is 1350 degrees Celsius, and it's important to keep a clean tube and set a plate or crucibles depending on how you put your parts to avoid carbon contamination. That's really the crucial thing. 316L is extremely sensitive to carbon contamination. If you have too much carbon in your material, you don't have a stainless steel anymore. And that will also affect sintering temperatures, deformation, and all that. So this carbon contamination is really something we need to avoid at all costs, and to avoid that, the setter and the tube really need to be clean. A few words about supports. That's a question that we really get a lot, so we thought we would detail a bit on this. The first thing is, if you need supports for printing, you will need them for the thermal process also, because sintering of stainless steel occurs at quite high temperature. 1350 degrees Celsius is a high temperature for stainless. It's relatively close to the melting temperature, and that means the material is relatively soft. And if you don't have those supports during sintering, it will deform, it will collapse under its own weight. So that means we need to print the support with the same material. We usually add a one layer gap between the support and the part so that they're not too much attached and can be removed easily. That's very common in FDM printing anyway. And if we feel we may have problems for separating the supports from the part, we can add a layer of ceramic between the support and the part. We can do that by printing with another filament, a ceramic filament, of course, but we do tend to find this quite a complex process. So we usually more simply just add a bit of ceramic powder between the support and the part. So we just separate them, put a bit of powder, and put the part back on the support. We also try to be careful about the profile of the part. If you have a very high part, or if you have a very high mass on top of the part, you may have deformation during sintering for that same reason, because the material is relatively soft during sintering and therefore might deform because of gravity. So you have a few examples here. Here you have a small part that we printed for a customer, and the geometry of the part meant we couldn't find a way to sinter it without support, so it would have deformed anyway. So we printed the support, which is relatively big and which was relatively dense. I think that the density was the infill density was 50 or 60%, so that it could support the weight of this part, which is quite heavy. You can see here with another angle how it worked. Another example here about support and printing strategy is this part which you can see here, which is a bracket that was asked by one of our customers, the Royal Dutch Navy. The first difficulty we had was that part was too big for our furnace. We couldn't fit it in the furnace. So we decided to cut it in two parts and to assemble them. And you can see here how we did that. We just separated here, made it self-assemble two-part structure, and with some supports here. You can see here a thin layer of ceramic that is just added before sintering, so that you can see how it looks like. Problem is this worked, but we did have some deformation because you have a part here which is relatively high. We did mention the fact that high walls can deform, and that's typically what you'll have. They just sagged on one side because of gravity during the sintering stage. So we had to rethink our approach, and we actually separated the part in three so that we could support better the bracket elements of it by flipping them on the side, as you can see here, which really makes for a much stronger support and avoids any high walls that can deform during sintering. You can see here how it works, and the fact that the second part had no deformation at all, while the first one had some deformation. Now, a few examples of applications to end this presentation, and then I'll be happy to answer your questions. So the filament was really launched very early, very recently, but we had some early customers trying either materials or parts that we printed for them, a bit of both. Here you have an example with MGB, which is a company specialized in bar turning, and they are using this material to print lubrication nozzles for bar machining. So basically, bar machining is a process for machining a high quantity of small parts like threads, inserts, and stuff like that. One of the issue you can have during machining is overheating of your part and poor lubrication that can damage either the part or the machining tool. And well, our customer wanted to make a custom-made lubrication nozzle. Problem was he couldn't print it in plastic because it was not resistant enough to pressure, and so he decided to print it in metal. You can cut the sound because that's a bit loud. You can see here how it looks like. This is the standard solution you have in the industry. The machine part is a small orange part we can see here is probably copper or brass or something like that, and usually spray some cooling fluid on it, but you can see that the cooling is quite imprecise. It doesn't really necessarily fall on the part. You don't have a high cooling effect, and if you want to be more efficient, you can use that kind of nozzle where you can see that really the cooling is much more performant. This is working at a pressure of 80 bars, and obviously that means very high pressure. I'm not sure you can see the part. It's right here in the middle of the picture, assembled on the equipment. So that does prove that the 316 material withstand very high pressure, is watertight. It is possible to add some thread tap on the top of the nozzle so that it could be assembled properly, and that makes for a very durable, efficient, and custom-made part. That part couldn't be machined, by the way, because of the internal channel you have in the part. You couldn't machine it. If you could machine it, of course, our customers, being a machine shop, they would have machined it. The second example is the one we mentioned. It's a helmet bracket. It's a small fixture that will be fixed on top of a helmet for some flying training sessions. And the interest here is just having a solution for a customer. The customer is the Royal Dutch Navy, and the interest for them is to have ready to use a simple method for printing parts on the spot, and printing parts with stronger mechanical properties than what they can have with thermoplastics. Well, that's really self-evident. The last example, again, the product is relatively new. We'll have some more use cases soon, but is an internal use case. The customer is ourselves. We use this stainless steel material to print nozzles for extrusion of our own filament. So how does that work exactly? We had a problem of abrasion of our own nozzles, which are usually made in tool steel, but our materials are extremely abrasive, so they used to wear down over time. So we had that idea of printing them in ceramic, of course, since we make ceramic filaments, but the problem was those ceramic parts used to break because there's a very significant pressure when we do extrusion. And so we ended up with a hybrid approach where we print the nozzle insert in ceramic and another shell in metal. You can see here the principle. You'll have an insert here, which is in ceramic, a conical insert that goes into this nozzle. That allows for wear resistance thanks to ceramic and to high pressure resistance thanks to G16L. That's it for the moment. If you want to see these materials in real life, you'll have a few occasions. Our next big exhibition is Formnext, but that's end of the year. Before that, we'll be in a few trade shows and conferences for ceramic manufacturers. We'll be at the ESES in July, and of course, we will keep doing some more webinars on the topic if you're interested to know more about this. So thanks for the attention, and I'll be happy to answer your questions if you have any. You can put your questions in the Q&A section on the top, and yeah, I'll try to answer these. So a question about how do we compensate the sintering process and keep the geometrical accuracy? Well, basically, this is not done in the CAD file. We don't specifically modify the drawing. We only oversize the part. That works really for most parts. That means if you don't have any specific deformation, you don't need anything more than the scale factor in X, Y, and Z, and that will be sufficient. Of course, some geometries are not possible. That's why we also have a design guide to say what's possible and what's not. And if you keep in the design guide, you should be able to have accurate part on the first trial. So no, I'm afraid I can't share information on how we make the filaments. That's proprietary information, and I'm sorry, but we don't share much about this. But I can say that we have several binding systems available at Nanoe, and we also have a thermal debinding material that does work well, but we decided to switch back to chemical debinding for those reasons I exposed. Carbon contamination, which was really an issue, hydrogen sintering versus argon sintering, and all of these. So that question on supports, I was pretty sure we would have some questions on supports. How do we apply ceramic layer between support and components? So what you find on the market usually is people will sell a second filament, which is a ceramic filament, so that you can just add one layer between the supports and the part, 1 or 2 layers. Most slicers will support this, so we could do that. It's just that we find this relatively complex. It adds a lot of complexity and time to the printing process, which is already relatively long. It adds some risk of failures to make it simple. So what we usually do when the part allows for it is we just print supports. After printing, we'll separate the support from the part. Actually, sorry, we will debind chemically first, which has to be done before. It also helps to separate the supports from the part. If they don't come out by themselves during debinding, which happens most of the time, we just separate them, which is relatively easy, and we add a thin layer of powder just by applying powder on it. We are considering selling a small solution on this. For the moment, we don't. We just recommend to use any standard ceramic powders, but we may offer a product at some point. So how homogeneous are the parts we print, and can we ensure there's no air gap between the printed layers? So that's really a big question, especially if you start looking for mechanical strengths. The adhesion between layers is absolutely crucial. And so, well, all this goes back to how you parameter your print. If you print with correct parameters in terms of extrusion, you can ensure a very good adhesion between layers and to avoid gaps. I'm not saying there's no porosity at all. There's always a few defects, especially with metal, which is um, uh, a bit more sensitive than ceramics to that kind of stuff. So there will be a few porosities in the part. That's something you have to know about this technology. And if someone tells you that they can print absolutely perfect parts with no porosity at all by FDM, I'm a bit dubious. So that's part of the trade-off of the technology. When we say that we reach 95% density, that's partially because of sintering, which won't get you to 100%, but also because of the printing process. But still, again, with the right parameters, you get to very strong, dense parts with good layer adhesion. And for most use cases we've seen so far, which is in the range of tooling, custom-made parts, but not necessarily the most critical component on the factory, that usually works really well. So how does it work with lattice structures and topologically optimized components? So lattice is something we use a lot. Of course, with FDM, you can use infills. We can barely see on the picture here a bit of a gyroid infill on the right side. Lattices are usually not a problem. If you can print them, they usually come out of sintering really well. They need to be self-supported lattices that you can print by FDM. Topologically optimized components is another question. To be honest, we haven't printed much of these parts yet. I hope to do so soon, but I would say should work fine, but you need to account for the process limitation. We did talk about the risk of deformation during sintering. If your topology optimization goes to very, very thin walls or very thin sections, it might cause a problem because of this sintering process. What do we need to have to do the debinding and sintering ourselves? So the first answer to that is, well, we do offer a complete solution with debinding and sintering. The cost for debinding and sintering equipment provided by Nanoe is 10,000 euro. So that might be an option. If you would like to use equipment that you already have, debinding just needs acetone. So you need a vessel where you can put acetone. If you want to speed up the process, you need to heat up a bit the acetone to 30 degrees Celsius. And you need the ventilation because acetone is volatile. For sintering, you need a furnace that allows an excellent quality of gas. That means no oxygen at all. You need to be in the range of ppms of oxygen. If you have more than that, you're going to have problems of oxidation. And that furnace needs to go to 1350 degrees Celsius. Question about the machines. I think I just answered it, but basically we use any printers with a preference for direct drive printers. The example, I don't know if there was pictures of the printer, but the printer we use the most is a Ray 3D printer, but I mean, usually any direct drive printers will work just fine. Debinding, again, is a simple vessel for acetone, and then sintering does require a high temperature, vacuum tight furnace. Can you share more details on the sintering process? One single ramp up to 1350 dwelling time and all that. So that's a good question. Actually, it's not to single ramp because in the furnace, we actually do a part of thermal debinding and then sintering. So we'll have a quite slow ramp up to 600 degrees Celsius, 500 to 600 degrees Celsius, where you have burnt off the binders, and then you can ramp up much faster to 1350. Usually the dwelling time at 1350 is 2 hours and cooling down. But the longest part of the process is actually the thermal debinding, which is going to take we usually say the total cycle time is 2 to 3 days. So can we use nitrogen instead of argon? I must say I don't have the answer. I'm not saying no, we just never tested it. That's an interesting question. We should test it. So a question about the fragility of the filaments. So yes, the filaments are relatively brittle because of the high volume loading of the filament. The filament will be brittle. So we just try to use adapted printers which have the right kind of extruder to avoid breaking the filament. So I don't know exactly what filament you have and what printer, so I can't get into details. But if you have the right printer, we also usually position the spool on top of the printer so that it just comes down directly into the extruder. And usually that helps a lot. But the most significant thing is probably the extrusion head. We should look at the kind of extruder you have. And one last thing is, I can't talk for our competitors, but if it's some of our filaments, we do have aging of the filament over time. So if you have filaments that are more than 1 year old, they are probably too brittle to be printed. Can you print metallic geometries of arbitrary shape? Yes. Well, that's really the idea of 3D printing. You can print any shape, of course. Yeah. So, do we have a comparison with other 316L filaments on the market? I don't like too much to go into comparison, but I can answer to that question briefly. So when you say other 316L filament on the market, there is one obvious player here, a very big one, which is BASF. There are a few other ones. If we talk only about the BASF filament, the BASF filament is a very good filament. Technically, it does work very well. It prints quite well. The printing temperature is quite high, but apart from that, it does print well. The drawback, I would say, don't know if it's a drawback, but the feature of this filament is the type of debinding they're using. They're using catalytic debinding and then hydrogen sintering. And that means that either you will have to outsource the post-processing, which they do offer, but if you want to do the post-processing in-house, the investment range is 10 times what we're offering. It's in the range of a few €100,000, 1 to 200,000 euros, to have an equipment to post-process the BASF filament. The main difference is we developed our filament so that they could be used with simple debinding procedures and simple furnaces, again, without this hydrogen atmosphere, which is really a difficulty. And that allows to lower the price of the equipment a lot. On the printability, I would say, I haven't tested a lot of the BASF, so I can't say, but probably comparable. But where we really focus is on having a post-process that's as simple as possible. Can we sinter 316L and ceramic using it as an insulator? So I guess you mean co-firing, mixing ceramic and metal and firing them together. It is a bit challenging. We haven't done that so far. When we need a ceramic and a metal, we actually usually print them separately, calculate the shrinkage really neatly, and then just assemble, just like we showed for the nozzle, and that really does work very well. So nitrogen gas instead of argon, I think I answered that. I said, I don't know, maybe, should try. Roughness after sintering. I must say, I don't think we have data on this yet. clearly the surface are relatively rough. You can see it on the pictures. I mean, we're not cheating here. You can post-process afterwards. If you need a shiny surface, you can tumble it or sandblast it or whatever. But the native roughness is what you get with FDM. You know. What do you use as material for support interface for complex geometries? That's a good question. That means when you can't just separate the support and add a bit of powder like that, how do you do it? Well, we would use our zirconia filament for that, which is a ceramic. Well, thanks a lot again for attending. If you have no other questions, I guess we'll stop the presentation today. Of course, I'm open to new questions if you have any, but if not, we'll